Hello everyone. Today's topic is Maxwell Boltzmann distribution. We have already seen three distributions in the previous video. Now we will see in detail how Maxwell Boltzmann distribution is derived. Now we are going to consider an isolated system of n identical distinguishable and weakly interacting particles contained in a volume V at an equilibrium temperature T. So the total number of particles is capital N. Okay, and the internal energy of the system will be U. Now in this case, we do not account for spin quantum number of the particles because it's a classical system. The particles do not have to follow quantum numbers. Okay, and also since the particles are also weakly interacting with one another, the potential energy of the system is 0 and hence the total energy is given by the kinetic energy of the particles, right. Now also the mean separation between the particles is larger than the thermal wavelength and therefore they are distinguishable. So since d is greater than lambda, the particles are distinguishable. So Maxwell Boltzmann system is a classical system and the particles are distinguishable. Since the particles are distinguishable, that means that any number of particles can occupy any energy level in the system. Is it clear? Okay, so here we have considered a system. Now let's go in the details. So let's say we have 1, 2, 3, 4 and so on up to L states, and the energy of these states are E1 for state 1, E2 for state 2 and E3 for state 3 and EL for state L. And the number of particles which can occupy these energy levels are respectively N1, N2, N3 and so on NL. Now remember, any number of particles can occupy any energy level in the system. So here the number of particles is very large. Here N is very large. That you have to remember. Now we are applying this enumeration to a classical case, right, where energy is continuous. So what we need to do is we must divide this energy into cells. Now in phase space we have prepared different cells, right. So the cell size we can choose of the dimension as we know is del P del X equal to H cube, right. Now here we are considering a gaseous system, right, ideal gas. So at a standard temperature and pressure, if you look at the mathematical answers, you will find that it is roughly 1 in a lakh chance that a cell is occupied, right. So if we look at any, let's say an S number of particles or state, S state, the number of particles and as it is most likely to be 0, or if there is any particle, the number of particles will be hardly 1 and 2, right. But here as I said, we are considering Boltzmann method, right, and here the N can be very much large and we can assume that N is very much large. Okay, so why do we need that? So that we have smooth change of state from one state to another state when differentials are used. So for that purpose we are considering that even the particles in a particular state, number of particles is very large. Now again we know that the number of states we have considered is L and the number of particles in those states are N1, N2, N3 and so on up to NL. So the total number of particles capital N is nothing but the summation of all these particles in the given states, L states, right. Similarly, the internal energy U can be given by summation I is equal to 1 to L Ni Ei, right. Now the total energy U and the total number of particles N of the system remains conserved, okay, and further the energy of level EIs, all the EI levels remains unchanged, they do not change, right? So their differential from 1 and 2, this and this, that is summation I is equal to 1 to L d n I is equal to d capital N is equal to 0, because they are conserved, they do not change. Similarly, d is also equal to 0. Is it clear? Okay. So now the next thing we want to do is we want to find, we have available states, we have available energies, and we have number of particles in those states, right? So now we want to distribute these particles in the available energy states. So there are number of ways to distribute the particles among the energy states, right? So in other words, what we are going to do is, the probability is nothing but permutability. Okay, we will see that soon. Now what we are going to begin with is, the first thing is we begin with the postulate of equal a priori probability. Okay, so what it tells us that each state, equal a priori probability tells us that each state or cell is equally likely to be occupied. That is, there is no preference over one state than the another state, right? That's why I can say that, or we can say that the permutability is a measure of probability. So in the equilibrium situation, distribution of particle has maximum probability of occurrence. Okay, so let us understand. Let's say we have total number of W of independent ways to distribute particles among the given states, right? So we have states from 1, 2, 3 and so on up to L, and the number of particles occupying those states are N1, N2 and so on. So we want to see how many independent ways this N1 particle can be distributed. Clear? So that will be the first task. Then when we find the number of ways, what we do is we find the set which has the for where the W is maximum. Okay. So the first state with us is, let's say, with energy E1. So we have first state with energy E1. We want to find the number of ways in which the N1 particles are chosen from N available distinguishable particles, right? Again, the first state we are considering is with energy E1. We want to find out the number of ways in which particles N1 are chosen from the available N particles, and these particles are distinguishable. Okay, so the number of ways of choosing the first particle out of N particle is how much? We have total N particles, so to select the first particle out of N, we have N choices. So the first particle is chosen from the N available particles. Correct. After choosing the first particle, now how many particles we have? We have N minus 1 particle. Right. So the number of ways of choosing the second particle is N minus 1. Then we are left with N minus 2. So the third particle, right, so the number of ways of choosing the third particle is available with us is N minus 2 and so on. So like this, when we move to the N1th particle, we have how many number of ways? We have N to find for the N1th particles, we have N minus N1 plus 1 ways available with us, right? So the number of ways of selecting N1 particles out of N is N into N minus 1 into N minus 2 into N minus 3 and so on, N minus N1 plus 1, right? So this is the equation that we get. Now multiplying and dividing this equation with N minus N1 factorial, we can see that the numerator becomes N factorial and the denominator is N minus N1 factorial, right? So this is the number of ways of selecting N1 particles out of N available particles. I hope you understood it. Now the number of independent ways of selecting n1 particles for the first energy state E1 is written as W1, right? It is nothing but n factorial upon n1 factorial into n minus n1 factorial. So this is very easy to understand. Clear? Now, as we discussed, now we have done our work for n1 particle for energy state E1. So how many particles now remain? Now we have n minus n1 particles. So for the state E2, n2 particles which are occupying state E2, the number of independent ways of selecting particles n2 for the energy state E2 is W2, which is given by how many particles are remaining? N minus n1. So it will be n minus n1 factorial upon n2 factorial into n minus n1 minus n2 factorial. Clear? Now similarly generalizing it, we find that for the else state, WL is n minus n1 minus n2 and so on minus n L minus 1 factorial divided by NL factorial into n minus n1 minus n2 and so on minus NL factorial, right? So we have these numbers W1, W2, W3 and so on up to WL. Okay, now we want to find the total number W of distinct ways. So W, capital W is total number of distinct ways of obtaining distribution of N1 particle, N2 particle, NL particle with energies E1, E2, E3 and so on up to EL. So the total distribution, the maximum distribution or the total of the system is given by W is equal to W1 into W2 into W3 and so on into WL. Is it clear? Okay, correct. Then we substitute the values. Okay, over here we see that we can simply cancel out numerator and denominator with each other of the next term, right? So what we are going to be left with is n factorial in the numerator from the first term, and in the denominator n1 factorial, n2 factorial and so on up to nl factorial, along with the second last term along with the denominator of the last term, that is n minus n1 minus n2 minus and so on nl factorial. Okay, so what over here we look at this equation, we find that this is nothing but minus n1 plus n2 plus and so on nl, correct? So what is that? It is nothing but capital N. So n minus n becomes 0 factorial. Hence we are left with W is equal to n factorial upon n1 factorial into n2 factorial and so on nl factorial, right? So simply the number of ways the distribution is done is a permutation, or the permutability is a probability measurement. Okay, so n factorial is the total number of permutation of the particles or atoms, right? Okay, now here we have not considered the degeneracy. We have considered that energy state E1, E2 and up to EL, these all states are non-degenerate states. Now let's suppose that these energy states are degenerating, right? Then we can say that we have degeneracy G1 corresponding to energy level E1, G2 corresponding to energy level E2 and GL corresponding to energy level EL. Okay, so for example, let's take we have some ith level, some ith energy level EI, correct, and it has how many particles? Ni, and the degeneracy is Gi. Now here we have Gi levels of degeneracy at energy Ei. That means each of the Ni particles can be in any Gi level. So let's say the Gi levels do not have any preference, the particle do not give any preference to levels. So what comes out is that we cannot distinguish between the Gi levels, right? Because there is no preference of occupying the degeneracy in this particular case. Since we cannot distinguish Gi levels, we have Gi choices, right? So Gi becomes choices instead of preferences, right? So we have Ni times particles. So how many particles are there? Ni. So for first particle in the Eith level we have Gi levels available. Then for the second particle in the Eith level we have again Gi level available. Like this we have Ni times Gi available. That means we have Gi to the power Ni ways of arranging Ni particles among the Gi levels, right? Right. That means for the total distribution in W, if we want to we include the degeneracies, it can be rewritten as W is equal to n factorial upon n1 factorial into n2 factorial into nl factorial into, for the n1th and particles in energy E1 we have G1 to the power n1 ways of arranging n1 particle in G1 levels, right? Similarly for the nth level we have GL degeneracies, then it has GL to the power NL ways of arranging particles in GL levels, right? Then this equation can be simply written in this form. This is very important equation, okay. Now again, so this is the distribution that we have. Now for the most probable distribution of n particles among L energy state will be the one for which W is maximum. So we want W to be maximum, right? So in mathematics, when can we say that it's a maximum? If we take its derivative and if it is equal to 0, we can say that it is maximum at that particular point, right? So the most probable distribution of n particles for which W is maximum, what do we do is we take the derivative of log W. Now here for large value of n, here we have particles value very much large, I discussed in earlier portion. So we know that n is very much large, so we are going to maximize logarithm of W rather than the W itself. So here we take the derivative of ln W. Now this is the equation, dln W is equal to 0. Again I can write it in this form for all the nth levels, correct? Okay. Then this is the general expression considering the summation of all the I is equal to 1 to L levels. Now using this equation along with the conservation of particle and the internal energy, which is equation number 3, let's go to the equation number 3 again. Okay, so this is our equation number 3. Considering this, dni summation I is equal to 1 to L, dni is equal to dn is equal to 0, and summation I is equal to 1 to L, ei dni is equal to du is equal to 0. Let's get back to the expression once again. So from equation number 3 and this equation, right, we can write this equation as summation I is equal to 1 to L del by del n I ln W minus alpha minus beta ei dni is equal to 0. Okay, so what we have done is we have introduced the restriction of the conservation of constant n and u, right? Total number of particle and internal energy is constant. So we have introduced those restrictions and we have added them to the ln W, each multiplied by arbitrary constant alpha and beta. Now alpha and beta in this case are Lagrange multiplier, right? So this gives us the most probable distribution in terms of this equation. Now to get a better understanding of mathematical aspect, I hope that you look into the concept of how to use Lagrange's multiplier. Okay, so alpha and beta are our Lagrange's multiplier. Now we will give it in equation number 5. Here equation number 5 must be true for individual increment of dni. So that is for each and every level it has to be true. right? That means for each and every level, the term within the bracket must not be 0. That means it should be maximum, del ln(w) should be maximum for each level. So what do we get is del ln(w) by del ni minus alpha minus beta I is equal to 0. Now this expression will be useful ahead, we will see it soon. Okay, now let's move ahead. We have now derived the w in as equation number 4, right? Now we will take the log of the equation number 4. By taking the log of equation number 4, you get this particular equation, that is ln w is equal to ln n factorial ln I is equal to 1 to L product gi to the power ni upon ni factorial. Okay, so you simply go to the next steps, simplify it. Now over here we have ln n factorial. So what we can do, we can use the Stirling's formula. I hope you are already familiar with the Stirling's formula. Okay, if you are not, kindly look into that. Next, so we use the Stirling formula and we get this general expression, right? Now once we have this, what we are going to do is we will differentiate this equation with respect to ni level. Why? Because we want to check for the each and every term. So what does that mean? When I am looking for the differentiation with respect to ni term, all the terms would be 0 except the nth term or the ith term, right? So by taking the derivative with respect to ni, what we get is this equation. Look at the equation. We take the derivation with respect to ni. So this term falls, first terms, and we have ln gi minus ni into 1 upon ni minus ln ni plus 1, right? Simplifying it, we get minus ln ni upon gi. Give it equation number 8. So from equation number 6 that we derived, this one I told you to remember, right? Okay, from that equation and our equation number 8, if you compare, we get ln ni gi, because this is also del by del ni ln w, and this is also del ln w by del ni. Okay, from these two equations we get ln ni upon gi is equal to minus alpha minus beta ei. Taking the exponential, so we will get rid of the logarithmic term. So ni becomes gi into e to the power minus alpha minus beta ei, so that ni is equal to gi into e to the power minus alpha into e to the power minus beta ei. This term is the Maxwell Boltzmann distribution of the particles among various states. Is it clear? So this is the derivation we have done for the Maxwell Boltzmann distribution. Remember, the particles here are distinguishable. The mean separation is larger than the thermal wavelength and they do not follow quantum law. Also remember that number of particle is very large in this particular case. Okay, so I hope you got a better understanding how this term, which you have been using widely up to this point, is derived. So please share this video with your friends. Stay safe, like and subscribe. If you have any doubts, any query, or you want to learn something, please write it in the comment section. Take care. Vande Mataram.